In this block, we're going to look at how functions become data in Haskell and the effect this has had on other programming languages. At a high level, you could say that functions as data is the USP, the unique selling point of functional languages. They take functions and we can pass them as arguments to other functions. We can return a function as a result of a function, or indeed we can write functions that do both. They take functions and return functions. We can write operators that do that, and often we call functions that do that combinators, just for historical reasons. What I want to do is show you the mechanics of this, how we can, some of the built-in operators, how we do return functions as results using lambdas, but also using partial application. And I also want to show some examples of putting this into practice. So abstractions that use functions in an essential way, and APIs that do the same. And this is one of the reasons that languages like Java and many others now have lambdas, because even if you don't use the lambdas for anything else, they help you write really effective, elegant, powerful APIs. So what we'll be doing is thinking of functions as data, just like any other data. Now, in particular, what we'll do is we look at some built-in operators over functions. We'll look at function composition and $ for function application. We look at how you write expressions that describe functions, that denote functions, using what's called lambda abstractions. We have seen this a little bit in the example of rock, paper, scissors, but I'll be talking about it in a bit more detail here. And then we'll look at partial application and how that's based on the idea of functions being curried. This is after Haskell B. Curry, who was the one of the people who invented this representation for functions. We'll be looking at how functions can be used to implement a library representing regular expressions. And then finally, we'll talk a little bit about recursion and functions that embody recursion.